class, before that, can you hear my voice? Hear me? Okay. Right. Thank you. Thank you, Yan Bowen. Right. So there are a few things that I would like to discuss with you because um, next week will be the week 8, right? Okay. So next week will be your midterm break, and then a week after that, you need to. We are going to have a face-to-face class. Since that there are few international students here, I think like this course will be run hybrid. Okay, so uh, those who are here, I mean like the local student, you need to come to the uni, okay, to attend the class, right? So and this course will be run in a hybrid mode, okay, because there are several of you, especially those who are international student, and you are going to make an arrangement, okay, to come to UM. But since that it is, I think like it's a very, I mean like, it's very like, I mean like, how can I say that? It's a decision, right? Like, it's been done a few weeks ago. So they ask you to come to UM. Either we are going to have a hybrid class or face to face. Okay, so I think like most of you disagree about this decision because I think like uh, almost all of you want to the class to be conducted online until the end of this semester. Okay, so next semester will be next a different story, but we have no choice since that the government already opened uh, for face-to-face class. They allow to have a face-to-face class. Therefore, University Malaya would like to implement for all the students to come to the lecture starting from week 8. So meaning that okay, we next week will be a midterm break. Okay, and then a week after that, you all need to come to UM to attend the class. Okay, so from 6 o'clock to 9 o'clock. All right. So any issue regarding this hybrid mode? Okay. So there will be no option like saying that you are living in KL, but you prefer to go for hybrid mode. I think like I don't think like it will work. Okay, so those who live in KL or live I mean like if you are a local people, okay, even you are in Johor or anywhere, you need to come back to UM. Uh, yeah, does remote learning? No, remote learning. We will have a hybrid mode. Okay, so those who are a remote learning student, international student who have problem to return to UM, this course will be conducted hybrid, meaning that there will be a face-to-face and also online class together, right? Hybrid, like online and face-to-face. Anything else regarding the implementation, week 8? No issue. Okay, so I think like most of you can make it, okay, because you are not just taking this course, you are taking few other courses as well. So I believe that some of you are so excited to return back to the university. Some of you prefer to have an online class until the end of semester. However, they already changed the system. They want you to come by week 8, so you have few more weeks to prepare yourself to come back to Right. So if there is no issue, okay, again, Z Han Yin, okay, for a remote student, you can attend the class online, okay, because this course will be conducted hybrid, okay, hybrid mode. All right. Yep.
Sorry, I just want to want try to ask, because some other lecturers say we cannot change the time from must start at 6 p.m. So is
Mm-mm.
it for this also same 6 p.m.?
6 p.m. as well. Yeah.
Oh, because I'm working at Klang, so is it okay like sometime traffic jam I will late
Uh,
a bit?
yeah, it's understandable, right? So I think like we will. I mean, like it's okay for you to enter slightly a bit because we can understand you are uh, heading like I mean having a traffic jam, right, or something. Mhm.
Thank you,
So
Doctor.
I think like last time this course is conducted from 6:30 till 9:30 p.m. But it's been I mean like it been adjusted to 6 o'clock to 9 o'clock. So I'm not sure about why they changed the time, but I think like 6:30 to 9:30. I think like everybody can make it because I mean like you can go. I mean like you can go back home. Uh, I mean like the reason they changed from 6 to 9 is because everyone can leave early. Okay, by 9 o'clock everybody's we finished the lecture. However, like I'm not sure. Okay, so I think last time the class is from 6:30 to 9:30 p.m. But now they already changed the time 6 to 9. Okay, so since then some of you have a problem like to come to UM due to traffic jam and everything. So I think like our class will start at 6 anyway, but we will. I mean like I will try my best not to. I mean like not to finish off my class within 1 hour. So I will definitely will wait for you because we will take the attendance. You know, we will discuss a little bit about any problem regarding last week, etc. Right? So I don't think that will be an issue for attending late to class. Right? Okay. Now, all right. So next week will be midterm break. Okay. So if you refer to the spectrum, I already released an individual assignment. Okay. So this week, okay, supposedly last week we are supposed to have a normal lecture. However, due to the public holiday, so no class. Okay. It is not allowed for us to provide you with the material or something because a public holiday is supposed to be a public holiday. Okay. Right. So and we are not allowed to conduct any lecture. Right. So today we are in week 7. Okay. And if you refer to Spectrum, I already uploaded a material regarding modeling in survival data. Okay. And you can also look at your assignment question, which is the assignment question is about the modeling survival data. Right. So I will share with you my screen. Okay. And I will about sorry. Okay, so if you can see my screen, okay, I'm now showing you my spectrum, right? So we are now in week 7. So I have listed down all the materials, okay? So since that it is Ramadan and I don't have, I mean like I cannot do a full stretch, 3 hours to conduct the lecture, but I have provided you with some of the materials, okay? So for today's class, right, I'm going to just give you a brief about what is the Cox proportional hazard model. Okay, that is actually a basic modeling in survival data. So we start with Cox proportional hazard model. And then you can also look at a material that I highlighted here, right? So once we discuss about this Cox proportional hazard model, you can read through about the fitting of the proportional hazard model and so on. Okay, by after you completed, I mean like it is actually restricted, but once you finish off the activity, you will allow to look at the materials. Okay. So there are a few materials here and it is very useful for your assignment. Okay. So and also before I leave the lecture, right, I would like you to do a lab 4 practical. Okay. So what I'm expecting from you, this is just an example for you to practice. And please submit your R markdown work uh, in the submission given below, right? So please submit your practical class, which is the lab for practical. Submit your work in R markdown today before 10 p.m. Okay, before we end the session, I will leave to you on how to do the practical class. Okay, so you can try it on. Okay, and then you can run it. You can look at the coding, and then you can compile it using R markdown. Right? Okay. This is your assignment. Okay, so I put this in a separate section. Okay, so this is your individual assignment. Okay, so you will be given 2 weeks to complete your assignment. This is an individual assignment, okay, not a group assignment. All right, so and also you will be given an R code, okay, where this time we are not using the library survival, but we are using library corps, okay. So in survival analysis, right, so we can either use a data set like a KMSurf, right, or we can also generate a survival data set. So for this assignment is actually uh, to give you an exposure that using we can use library package COGS to generate the survival data sets, right? And then from the data, you can analyze by following the instructions, right? I hope everyone would be okay with that. Okay, so let us look at our first lecture notes. Okay. Oh, sorry. Before that, I don't think I'm going to open it in Chrome. Okay, hang on just a bit. Mm, view or change. Okay. Hang on, I just received a notification that some of the lecture recording will is going to set to expire, so I need to change the setting. You mind to wait around 5 minutes? Okay. Do you have any problem with your tutorial too so far? No? All right, so let us look at our lecture note regarding the Cox proportional hazard model. Okay? Okay, so just to recall you that when we are using a log rank test, it's actually a test to compare between two groups. Okay, so we can also extend to more than two groups using the log rank test. Okay, and besides that, we also have Wilcoxon test as well, right? So let us refer to this lecture note about modeling survival data. So modeling survival data is to for survival data with the explanatory variables, right? So modeling hazard function comparing two groups without covariates. So the first thing that you need to do, you need to assume the proportional hazard assumptions, right? So what is the proportional hazard assumptions? Okay, anyone would like to, what is the assumption for proportional hazard? Okay, so I'm not going to give you the answer. Please refer what is the proportional hazard assumption. Right, so proportional hazard or Cox regression model say that HNT equals to the psi HST. Okay, what is psi? This is the hazard ratio or the relative ratio. What is the HNT? HNT is the hazard of death for patient on new treatment, while HST is the hazard of death for patient on standard treatment. Okay, so when we want to find the hazard ratio, we use formula in equation 4.1. Okay, so right, so for any negative, non-negative value of t and a constant value of your psi. Okay, so these are the two indicators. If your psi is less than 1, okay, meaning that the hazard of death at t is smaller for an individual on the new drug relative to an individual on the standard drug. Okay, so that is the meaning when you have psi which is less than 1. Okay, how about if you have psi which is greater than 1? Okay, so if you have psi greater than 1, meaning that it is for individual, meaning that the hazard of death for an individual on the new treatment is higher than individual on the standard drug. Okay, so this is how we are making a comparison without any covariates, right? We are using the hazard ratio. Okay, all right. So this is an example on how we are making a comparison, right? Okay, alternatively, okay, the HIT is the hazard function for the ith individual, and H null T is the hazard function for an individual in the standard treatment. So we can also have, instead of having a new treatment and a standard treatment, we can also make a hazard um, ratio or for individuals as well. Okay, so in this case, HIT equals to psi H null T. So you can make a comparison of hazard for individual as well. Okay. All right. So in this case, since your psi is greater than 0, Okay, then the hazard function for the ith individual is given by HIT equals to e to the power of beta x h null t, right? What is I? I is for the individual who in the new treatment, and null is for individual in the standard treatment. So your I can be from 1 until n, and your n is your sample size. Okay, so that is how, if we want to make a comparison between two groups without any covariates. Okay, and then if you want to test them, you can use the log rank test to do the hypothesis testing about comparing two groups. Okay. So the next one is the proportional hazard model with the covariates. Okay, so the hazard of death at particular time depend on the value of x1 until xp. Okay, where p explanatory variables. Okay, so we have a hazard of death for p explanatory variables. So x1 until xp. Okay, so let x equals to x1 until xp. H null be the hazard function for an individual on the baseline hazard. So this is the new hazard function for ith individuals, right? So HIT equals to psi xi. What is xi? Xi is for the xi is your x of your I individual, and H null t is actually the hazard function for baseline treatment. Okay. All right. So psi in the bracket interpret as the hazard at time t for individual who vector of explanatory variable is xi relative to the hazard for an individual whom x equals to 0. Okay, so we are making a comparison between two types of treatment for ith individual, right? Okay, so again, we are still under the comparing two groups with covariates. Okay, since the psi xi is greater than 0, then the hazard function for the ith individual is given by HIT equals to E nu I H null t, right? What is nu I? Nu I is your linear component of your model, which is beta 1 x1, beta 2 x2 until beta p xp. Okay. So if we rewritten equation for for model 4.5 means equation 4.5, we can written as log HIT over H null t, okay, which is equals to nu I, okay, where nu I is your linear component, okay. Right, so here, how do you get that? Okay, so from 4.5, sorry about that. So okay, so HIT, okay, over H null t equals to the E of nu I, right? Okay, so when you log on your left, you will get a linear component of your nu I then. Okay, so log of your HIT over H null t equals to nu I, which is your nu I is equation 4.6. Okay, so that is how we get the hazard function for covariates. The next one is the linear component of your proportional hazard model. Okay, there are 4 types of variable, which is variates, factor, interaction, and mixed term. Okay, what is variate? Variate only takes numerical value of continuous scale of measurements such as age, blood pressure, etc. How about factor? Factor takes a limited set of values known as the level of factor. Okay, such as sex with 2 levels of male and female. Okay, so factor and variates is a bit different. Okay, variates is like a continuous variables. Okay, you can also factorize your variates. Okay, if you set into a certain limit. Okay, but factor is actually like a categorical data. Okay, for example, sex. Okay, or gender. you can have male and female. So you can set 0 as male, 1 as female. Okay. So if you set 0 as male, meaning that you let your baseline is male gender, right? And 1 is your level 1. Okay. And how about interaction? So it's a mixture of effects of combination 2 or more factors. So interaction can be 2 or more factors, right? How about the mixed term? Okay, so it can form from a factor or a variate. Okay, we can see a different effects of a variate in different level of factors, right? Okay, so this is the normal linear component. It's not only in PHM, but this is actually applies to all statistical modeling, right? Now, let us start with the continuous variable where we include a variate in our PHM. Okay, what is PHM again? It's a proportional hazard model. Okay, so let's say your x1 and x2 are the continuous variable or variates with x1i and x2i respectively respective value for the ith individual. Then the proportional hazard model for the ith and the n individual is HIT equals to the exponential of beta 1 x1i plus beta 2 x2i H null t. Okay, so that is how you include a variance in your model. Okay, so your new is actually beta 1 x1 plus beta 2 x2, since that you only have x1 and x2 as your variance, okay, as your covariates. Okay. The next one is to include a factor. Okay, so say that a factor A has k level. Let your alpha j be the main effect of the jth level of factor A. So in the PHM, the hazard function for an individual with factor A at level j is given by exponential of alpha j H null t. Okay, so what is your alpha j? Alpha j is your main effects. Okay, so to be consistent with the definition of H null t, one of the alpha j should be 0. Like I said earlier, like if you have two levels about gender, right, which you have male and female, we can have 0 to 1. Okay, usually like it's a basic practice, like we can have level 1, 2, 3, etc. But to be consistent, we can have a baseline. So I think like it's a normal practice in survival analysis to set a baseline factor. Okay, say alpha 1 equals to 0, right? So this one, I just say it's a baseline. Okay. Right, so a baseline level. Right, so define. Okay, just now you said that we have k level, right? So since that we set the first level as 0, therefore we define k minus 1 indicator variables z2 until zk. So the values taken by each variable are as follows, right? So we cannot have z1 anymore because z1 is our baseline value. Okay, so we can start with z2 until zk, right? Because z1 is our baseline, right? So here is how we define the indicator variables. Okay, so Z2, okay, seems that the remaining is 0 except at level 2, right? And then for Z3, it is 0 elsewhere, but 1 at level 3 and so on. Okay, up to Zk, where we have 0 elements for your vector k except at level k. Okay, so this is how we represent the indicator variables for your factor. Okay. Now, treat each zj as a variate with alpha j as a coefficient and can now be included in your PHM. Okay, so factor A is said to have k minus 1 degree of freedom since there are k minus 1 parameter associated with it. Okay, so this is how you include a factor in your model. Right, so the next one is to include an interaction in your PHM. So what is interaction? Interaction means that you can include more than 2 factors in your model. Okay, say that A is a A and B are 2 factors with A 2 levels and B with 3 levels respectively. Okay, and your with alpha J and beta K. So alpha J is your for factor A and beta K for factor B. Right, so here is your level A and this is your level B. Okay, so here we will have 2 levels and 1 level will be set as a baseline. So therefore you are going to have only U2 here. Okay, where 0 for level 1 and 1 for level 2. Okay, this is for factor B with 3 levels where we set level 1 as your baseline and therefore you only have level 2 and indicator 2 and indicator 3. Okay, where for indicator 2, the first level is always equals to 0. Okay, and then this is for indicator 2, meaning that level 2 will be equals to 1. And also for V3, level 3 will be 1 and 0 in the 0 in your vector elements, right? So if you want to include the interaction, meaning that you get the interaction between A and B, this is the possibility, right? So these are the combinations, right? So you are going to have U2 V2, U2 V3, and also these are the combination of between level A, B. Okay, right, so this is for the first level with the first level in level in factor 2 in factor A and times with the indicator from level B, right? And also for level 2 in factor A with times with the level B. So this is how we get the indicator, interaction between 2 factors. Okay, so in this case, you are going to have 2 degrees of freedom. Okay, why is it 2 degrees of freedom? Because it's 2 minus 1 times 3 minus 1. Okay, so it's 2 times 1, which is equals to 2 degrees of freedom. Okay, so it is equals to k minus 1, right? So it's 2 minus 1 times 3 minus 1. So which is equals to 1 times 2, which is equals to 2 degrees of freedom. Okay. Right, so this is the last part, which is including the mixed term. So mixed term can have a variate and also a factor. So in this case, says that we have 6 patients with variate X and factor A. So this factor A has 3 levels. So these are how we do a combination between a variate X and also a factor A. Okay, so level A, you will have 2 indicators, V2 and V3. Okay, seems that level 1 will be equals to 0. And also you are going to have level 2 and level 3, right? So this is how you get your combination between a variance and also a factor A. Okay. Now, referring to this table, please look at example 3.1, which is about the prognosis for women with breast cancer. Okay, so you can refer to this real data set for prognosis for women with breast cancer. And this is how we get a mixed term for PHM, right? Any problem so far? Okay, since that we have 6 patients, so we just list individual 1 until 6, and you have level A, right, which is 2 level, 2 uh, one factor with 3 levels, and we assume that level 1 is our baseline. So that is why we are going to have level 1, 1, 2, 2, and 3, 3 here. Okay, so here you are going to have x1, x2, x3, x4, x5, and x6, right? So for level 1, everything is equals to 0, right? For level 2, you are going to have only x3 and x4, right? For V2, indicator V2, okay? So which is equals to 1, 1 here. While 3, okay, is for x5 and x6, okay? So any questions so far regarding this example? Anything that confused you? Right, so I hope that there is no issue regarding why is it 1, 1, 2, 2, and 3, 3. Okay, right, since there is no question regarding this example, shall we proceed to the model, right? So the model is HIT equals to E beta XI H null T, and H null T represent the hazard for women with negatively stained tumor. Okay, so here is actually we can use S plus, okay, and then you can also change it to R. Okay, so you can use Cox pH, SIRF, time status, dollar stain, breast cancer, method, breast load. So the same between S plus OR. Okay, so in this case you can also use R, the same command, and you can also get the output. Okay, so last time we used SIRF-FIT, right, to get the survival fit for our survival function. But now we are changing to using the function Cox pH. Okay, so Cox pH is actually for Cox proportional hazard model, right? So Cox pH, SIRF, time, status, okay, and then this is your covariate, okay, which is your X, stain. And then we are taking the data from breast cancer data set, and we are using the method breast load. Okay, so there are several methods here, okay, which I think like I'm not going to demonstrate the Cox pH model, which you can try it on in your lab for practical, where you have to submit your work before 10 o'clock. Explore how many methods available for Cox pH, right? So this is the outcome. So in your summary output, they will provide you with the coefficient, okay, which is your beta, right? This is your beta I, and then the exponential of your beta, okay? So I can put here your beta. This is your E of your beta, okay? And then you can also get the SE of your beta, okay? This is the SE of your beta. And you can also get the Z-test and the p-value, right? So from here, what is your interpretation when you compare your p-value with with your alpha 0.05, and also this is for the variable stain, okay? And this is the p-value for your whole model, okay? And how many observations that we have for the breast cancer data? N equals to 45, okay? And also you can obtain the likelihood ratio test here as well, okay? Which is the likelihood ratio test is equals to 3.87. Okay, try this on exercise for lab 4 later. Okay, so the estimated hazard ratio psi is equals to 2.48. So we are looking for the expected of beta, right? Because remember that your HIT equals to psi H null T, right? And this psi is equals to exponential of beta, right? So the estimated hazard ratio is 2.48, which is here from the output. Okay, in a conclusion, a woman who has a positively stained tumor will have a greater risk of death compared to a woman whose tumor who is negatively stained. Okay, so in stain variable, you have positive and negative. So in this case, it means that your HI is greater than 1. Sorry, your psi is greater than 1. Okay, so your psi here, your psi is greater than 1. So what does it mean by psi is greater than 1? Okay, so the HIT has a greater risk than the standard treatment. Okay, so in this case, a woman with the positively stained tumor will have 2 times higher risk than to those who is a negatively stained. Okay, so you can calculate your standard error of your hazard ratio. So the standard error of your hazard ratio is equals to psi hat times with your SE beta, okay, which is equals to 2.48 times with 0.501. You will get this value. And you can also calculate the confidence intervals for your beta and for your hazard ratio. Okay, what is the 95% confidence interval for your beta? So it is equals to beta hat plus minus, because this is 95, that is your Z alpha is equals to 1.96 and your SE beta is equals to 0.501. Okay, beta is equals to 0.908. So you will get between negative 0.074 and 1.89. Okay, and you can also calculate the confidence interval for your hazard ratio psi, okay, where the hazard ratio psi is equals to the expected of your beta, right? So once you get the confidence interval for your beta, you can easily compute your 95% confidence interval for your hazard ratio. Okay, so just plug in these two values, right? So it is between E of negative 0.074 and E of 0.189, which is between 0.928 and 6.619. Okay? Right, any questions so far? Okay, so if there is no
Sorry,
question,
doctor.
yeah.
Uh, come back to the table just now. I'm not sure if am I understanding is correct or not. So for the V2 and V3, the V2 and V3, is it come from the level 2 and level 3?
Yeah,
Oh,
because level 1 will be considered as baseline.
oh, so for the level 2 is the meaning is the middle stage, or
What do you mean middle stage?
the level 1, level 2, level
Okay.
3.
Okay, so for example, if say that we have a gender, right? So gender is in factor. So we have 2 levels, right? So we have male or female. So how do you define your baseline? For example, we define male as our baseline. So we are going to have indicator of a female only. You got what I mean? So you are not going to have V1 and V2. You are only have V2 in your indicator variables.
Oh, so here the A is not like do not have other meaning, the A here.
A have 3 levels, but you are not going to list out all 3 levels. Okay, so for the indicator, sorry, I just go back to the previous lecture note here, how we define the including a factor in PHM. So you are having a main effect alpha J with J level for factor A. Okay, and then for the definition of the standard treatment, you must have a baseline. So we should set alpha 1 equals to 0. The first level as 0. So to be consistent, right? So that is why we are going to have K minus 1 degree of freedom. Okay, so in this case, you are not going to put V1, V2, V3. You only can have indicator variable V2 and V3 only, if that factor has 3 levels. Okay, so look back at how to include a factor in the previous page, this page. Okay, so that is why we don't actually define first level. We always define first level as the baseline level, right? So we start with indicator variable Z2 until ZK onwards. You got what I mean?
Oh, okay. The baseline from 0, so not included the first level.
Yeah. So this is actually your indicator variable Z. Okay.
Okay, give me doctor.
All right. Okay. So where are we? Okay. Let us look at this example. Example 3.2. I think like if you refer to example 3.1, you can have a more clearer picture on how to calculate this table. Okay. Right, so let us move to example 3.2, the survival of multiple myeloma patients. Okay, so refer to example in the textbook about the survival of multiple myeloma patients. So these are the given variables. Okay, you have age, sex, M, okay, BUN, CA, HB, PC, and BJ. So age is actually a variate, which is a continuous variable. So the age of patient. Sex, M, okay, so this is actually the gender of the patient. So in here, we put M here because we set male to be our baseline and one to be your female, okay? And then BUN is actually the variables for blood, urea, nitrogen. CA is for the serum calcium, HB for serum hemoglobin, PC is the percentage of your plasma cell, and your BJ is the Benz-Jones protein, where this is also a factor where we set 0 as an absent protein and 1 as present. Okay, so how we define our proportional hazard model by including all these variables. We will set the PHM equals to HIT equals to the exponential beta 1 H1 plus beta 2 X2, which sex M1, MI, sorry, beta 3 BUN, beta 4 CA, beta 5 HB, beta 6 PC, and beta 7 BJ H naught T. Okay, so this is how the PHM model looks like. So since that you have 7 variables here, you will have 7 coefficient of your beta variables here. Okay, beta coefficient, sorry. Okay, so the H naught T represent to individual who is male, age 0, and has 0 value of BUN, CA, HB, PC, and also Benz-Jones protein. So this is how we define the baseline, right? So H naught T belongs to a male because male is our baseline, okay? And then 0 value of BUN, CA, HB, PC, and also 0 value for Benz-Jones protein, right? So this is how we get our R output. Okay, so I just change here, right? Because last time we used S plus, right? Now we use R output. So again, we use the function COX-PH, right? This is how you get the survival function, right? So serve time status, age, this is your variables, okay? Include all 7 variables in. And then what is the data? Data is a myeloma data. And we are using a method, Breslow. Okay, so this is the output. Okay, you have the column for coefficient, column for beta, column for your psi, and then the SE for your beta, and then you are having the Z test and also the P value, right? So also P value of your model, which include all 7 variables in, and also the number of observation N, okay? Okay, so here you can also look at the p-value for each of your variable x and compare it with alpha equals to 0.05, for example, okay? Any problem for example 3.2? Okay, so if there is no issue, let us move on to the example 3.4. So this is actually an example which involves variates and also a factor, a mixed term. Okay, there is no interaction term here, right? So let us move to example 3.4 about the treatment of hypernephroma. Okay, so we have two variables, which is neph, a factor, nephrectomy. We have two factors, 0 for no and 1 for yes. And then we also have another factor for age. Okay, so we have three different age group, which is age less than 60, and then level 1 will be 60 and 70, and level 2 for age greater than 70. Okay, as I said earlier, okay, even though you have a a continuous variable, you can also level them. So this example show you on how to level the continuous variable. So in this age, we are not interested with the real value of age, but we want to look in your age group. What happened in that age group? Okay, so we define 0, a baseline for less than 60. Okay, and then 1 for between 60 to 70, and 2 for greater than 70. Right, so here we need to introduce two extra explanatory variable for age group, H1 and H2. Okay, so in this case, we are going to put H1 for age group 60 to 70, and H2 for a patient which is greater than 70 years old. Okay, for interaction term, we will include two extra explanatory variables, which is also introduced, nephrec, nephh1 and also nephh2. Okay, since that you have a factor with 3 levels, and nephrec is a factor with 2 levels, we are going to include the interaction terms. Okay, so we are going to have nephh1 and nephh2. Okay, so this we can fit several models. Okay, so in this case, we are only we only have a model which consists variable age only. Okay, which we don't include variable neph in our model. Okay, so this model, the model 1, M1, is age only. Okay, age only. So this is the output for a model which consists only age. And this M2 consists variable neph only. Okay, so it's only consists a variable of neph. Right, while model 3 here, okay, consists a variable of age and neph. Right, so you can see there are 4 models altogether, where the 4th model include the interaction term. Okay, so M4, we are having the age, neph, and interaction. Interactions, right? So you have neph H1 and neph H2, right? So this is the full model, right? So again, this is the model which only consists age. This is the model which only consists neph, and this is the model which only consists age and neph with no interaction, while this is a model, a full model, which involves interaction between factor 1 and factor 2. Factor neph and factor age, right? Okay, so and you can also make a comparison what happened to the p-value of your model. Okay, so you can comment is the model p-value is getting smaller, and also you can make a comparison between each variables, right? So in this case, since that neph 2 level and age 3 level, how many degrees of freedom for this model, you are going to have 2 degree of freedom. So, right, because it's 2 minus 1 and 3 minus times with 3 minus 1, which is 1 times 2. Okay, so the degree of freedom is equals to 2 minus 1 times with 3 minus 1, which is 1 times 2, right? So that is your degree of freedom. Okay, so any questions so far? So we can see the full model gives the better p-value, where you can see the p-value for for M3 and M4 is slightly better compared to not really, right? This one, yeah, but this is significant at alpha equals to 0.05, right? But when you look at when you compare M1 with M2, which one is better? M1 and M3 and so on, right? So this is how we look at the p-value for each of the model. Okay, and you can also make a comparison by looking at p-value for each variables, right? Okay, so these are the example on how we can have how many types of models. Okay, so here we can have up to 4 models. Okay, where the 4 model consists an interactions, right? All right, so any question before I move on to the maximum likelihood? Okay, so some of you might ask, like, why use the method Breslow? Is we are going to talk about the method Breslow in the maximum likelihood for estimating your beta coefficient. All right, so here, find the likelihood of the sample data. Okay, suppose there are R distinct death time and N minus R right censored survival time, and assume that these there are no ties in this data. So this is a very common assumption. Okay, we don't actually assume ties in our data. Okay, so let Tj be the jth order of death, since your you order them T1, T2 until less than Tr. Okay, and your Rtj be the set of individuals who are alive and uncensored at time just prior to Tj. Okay, now consider probability of individual with variable xj dies at Tj. Okay, conditional on 1 death at Tj, okay, which is equals to probability of individual with variable xj dies at Tj divided by probability of 1 death at Tj. Okay, so how can we get this to this, right? So probability of x probability of individual with variable xj dies at Tj is actually probability of 1 death at Tj is actually a subset of probability of individual with xj dies at Tj. Okay, so that is why when we have probability of individual dies at Tj intercept with probability 1 death at Tj, it is equals to probability with individual xj dies at Tj. So this is actually a subset of this, right? So this is equal, the probability of individual with variable xj dies at Tj is equals to Hitj, right? Divided by probability of 1 death at Tj, it is equals to the summation of Hitl, right? Where your L is in Rtj. Okay, what is Rtj? Is the set of individuals who are alive and uncensored at time prior to Tj. And then, okay, as shown by Cox 1972, the relevant likelihood function for proportional hazard model is equals to the, what do you call this? Right, so this is actually, I cannot remember this, okay? Can someone help me this? Okay, so it is exponential because the Hij, because you are looking for a likelihood function. So Hij equals to the this is the psi xj over the summation of psi x xl. Okay. Okay. Right. So this is using the multiplication rule of the the likelihood function. Have you seen the likelihood function? So I think like when you learn probability and statistics, okay, we will come across to the likelihood function, right? And to calculate the likelihood, which is L beta, which is equals to the the product of the probability of individual dies at xj divided by probability of one death at tj. Okay, so that is the likelihood function. What is xj? Xj is the vector of covariate for individual who die at jth order time. Okay, tj. It is usually referred as a partial likelihood function. So this is not a full likelihood function. This is a partial likelihood function. Now, let T1, T2 until Tn denote the survival time for n observed survival time. So further, we let delta I equals to 0 for I time when it is right censored and 1 otherwise. So therefore, equation 4.8 can become like this. Okay, so L beta equals to product of exponential beta xi over summation of exponential beta prime xl to the power of delta I. Okay, so again, 0 for the ith time is right censored and 1 otherwise. So this RTI is actually the risk of set of time TI. Okay, so to solve this equation, right? Equation 4.8, okay, we want to get okay, for equation 4.8, sorry, okay, we can bring delta I down here by taking a log value. So log L beta equals to the summation, right? Because the product can change to summation now. Okay, summation of delta I times with the beta xi minus log summation of exponential beta I xl. Okay, so using the Newton-Raphson procedure, we can find the MLE of your beta hat. Okay, so we can estimate what is the beta hat using the Newton-Raphson procedures, right? Now, we just assume that there is no ties in the treatment. So what happens if there is ties? Okay, so what is that? So when death and censored times are tied, okay, it is assumed that censored survival time occur after the death, right? So when 2 or more deaths occur at one time point, equation 4.8, okay, what is equation 4.8? Which is here, okay, need to be modified. Okay, one way is through approximation. Okay, so let Sj be the sum of each for P covariate for those individuals who die at time J, where Tj equals to, who die at J death time, Tj. Okay, remember Tj is the ordered time, right? For your J equals to 1 until R. So if there are dj deaths at time tj, then the H element of Sj is Shj equals to the summation of your Xhjk. So what is Xhjk? It is the value of the H explanatory variable, where your H equals to from 1 until P for the case of dj individual. Okay, so K equals to 1 until dj, a person who died at J's death time, where J equals to 1 until R. So these are the Breslow method that we have mentioned in our code. Okay, so Breslow proposed the following approximate likelihood. So it is slightly different from equation 4.9, 4.8, where L beta equals to the product of J from 1 until R exponential of beta prime Sj over the summation of exponential beta prime XL to the power of dj, where dj is the death at time tj are considered to be distinct and occur sequentially, right? So now you know why there are several methods used, okay, which you can explore later during the practical lab, which you have to submit later, where I'm giving this practical lab for you to try on, right? So try to look at the practical session, right? So I have provide you with the example, etc. So just follow step by step, okay? Especially to introduce you on how to use the Cox pH function, right? Okay, so there are also several methods that you can choose. You can also refer to the help, okay? So I think for your master's level, we can just touch until the Breslow method, right? Okay, so we just use Breslow all the time. All right, so I think that's all for today's class, right? So you can do your exercise, like practical lab 4 when I later, okay? So the submission, so I'm expecting you to submit the exercise, right, by before 10 o'clock today. Right, so before we end our session, is there any question regarding this lecture note? Okay, so if there is no question, I think I'm going to end the session. Don't forget to do your lab 4 practical session, right? Does any question? Any question? The time is 21. What do you mean the time is 21?
Doctor, can I ask something about the practical? The lab for practical I have to submit it. So we will need to do it in R Markdown format, is it?
Yeah.
So when
yeah. So what I'm expecting, yeah, in either PDF or Word. Yeah.
Or either PDF or Word. Okay.
Yeah. Yeah. So I think some of you, so this this submission is not going to be evaluated, right? But what I'm expecting is actually I want all of you to submit your work, right? Because I think maybe like in future, like maybe to help you, let's say you are getting your final result to be at the borderline, so maybe I can refer to this lab practical submission as well, right? To help you during your critical time, okay? But this time around, I'm not going to evaluate your lab 4 practical because I don't have time to go through the lab 4 session together with you. So I'm expecting all of you try to follow the example using the R code given. Try to produce because my objective is actually to get all of you familiarized with function Cox pH, right? So once you run the code, you can just simply knead it using the R Markdown, okay? And this R Markdown can be saved either in PDF format or in Microsoft Words, right? So if you have any issue, you can just simply post it in group, okay? So I think that's all for today's lecture, right? I hope that I will end the session and you guys will continue with the practical session, okay? So the time is 21. Oh, okay. So I will change the submission time to 10 o'clock. Okay. All right. So I will change the time. Okay. I will change to 10 p.m. because I put the notification 10 p.m. Yeah.
So just now I checked the spectrum. The lab section 4 is not related to the lab 4 practical.
I cannot hear you. There is a lag.
The lab section 4 is not regarding to the lab 4 practical.
Shanzi, I cannot hear you.
Sorry, doctor, can you hear me? Hello?
Yeah, yeah.
Oh,
Sorry, like
okay.
I have bad network quality.
So just now I checked the lab section 4 is spectrum. So both of them are not the same.